I'm Fars Al-Kateri, I'm an electrical engineer.
I am Mohammed Al-Mansouri and I am a mechanical engineer.
My name is Andre Coelho and I'm a biomedical engineer.
My name is Paul Drust and I'm a mechanical engineer.
My name is Adrian Sacripanti and I'm a systems engineer.
My name is Kylie Slater and I am a biomedical engineer.
According to a 2010 CDC report, Arizona, Texas, and California account for nearly 43% of heat-related fatalities in the United States. Our goal is to create a wearable cooling device that can cool the user for at least 1 hour of non-impact athletics. Our device must be lightweight, weighing less than 1.5 pounds or 0.68 kilograms, compact, with a profile of less than 100 millimeters by 120 millimeters by 5 millimeters, wearable, devoid of sharp edges, and finally low cost, with each unit costing less than $100 to produce. Our design is based on the Peltier cooling module, a thermoelectric phenomenon that is illustrated conceptually on the diagram to the right. We will discuss this phenomenon in more detail throughout the presentation. Once again, heat-related illness remains a significant problem here in the Southwest. Our team was tasked with creating a wearable cooling device that can effectively cool the user for at least 1 hour of non-impact athletics. Our device must be lightweight, compact, wearable, and low cost.
Thermoelectric coolers operate using a phenomenon known as the Peltier Effect, named after the French physicist who first discovered it. It was discovered that as current is passed along a junction, in which each side of the junction is made of a different material, the positive terminal will get cold while the negative terminal will get hot. Thermoelectric coolers, such as the one used for our wearable cooling device, maximize this effect by having several narrow band-gap semiconductive metals lined in parallel and surrounded by ceramic coating. Heavier elements, such as tin, are commonly used in thermoelectric coolers due to their high electrical conductivity and low thermal conductivity to prevent heat from the hot side to bleed over to the cold side. The temperature of the cold side is dependent on the difference in the temperature difference between the positive and cold terminals, which in turn is dependent upon the current applied. A thermoelectric cooler that utilized the Peltier effect was highly desirable for the wearable cooling device for a variety of reasons. It is lightweight and low cost. This is due in part to its ease in manufacturing. Additionally, thermoelectric coolers have an extremely high lifetime, topping out at around 100,000 hours before failure. This high lifetime allows for the thermoelectric cooler to be reusable as well. We were also able to fully utilize the benefits of the Peltier effect at low currents, allowing the wearable cooling device to be safe for consumer use. One major drawback of the thermoelectric cooler is that the negative terminal needs to be cooled in order to maintain the Peltier effect. To achieve this, the wearable cooling device also has a heatsink and fan attached to it. For the heatsink, we chose aluminum because of its relatively high thermal conductivity and low weight. The fan was attached to the top of the heatsink in order to increase the convection of air around the perimeter of the heatsink's fins. Together, the fan and the heatsink have proven to be quite effective in keeping the thermoelectric cooler chilled. Many of the parts of our device, such as the plate and battery case, were 3D printed using a PLA ABS blend because of the material's light weight and rigidity. Wires are ran through the fins of the heatsink and then connected to the switch that the user can then operate. All 3 of the parts shown are attached to each other via epoxy. The heatsink performs the best, meaning pumping the most heat away, when there is a fan blowing air over its fins. Additionally, the length of the fins affects the performance of the heatsink. Taller fins increase the amount of metal exposed to the flowing air, which in turn increases the amount of heat that the heatsink can pump away from the Peltier module. In order to design the system properly, we first needed to determine the amount of heat the human body produced during exercise. Using the steady 1D heat equation, we were able to derive an expression for the heat produced by the body, where omega is the perfusion rate, rho is the density of blood, C is the specific heat of blood, TA is the arterial temperature, K is the thermal conductivity of tissue, and Qm is the heat produced by muscles. From this equation, we found that the human body can produce up to 0.11 watts per square millimeter of heat during exercise. It was also necessary to determine how much heat the wearable cooling device can pump away. We were able to quantify both the conductive and convective heat transfer using the corresponding equations, where K is the thermal conductivity of aluminum and H is the convection coefficient. Altogether, it was found that the wearable cooling device can pump a maximum of 3.9072 watt per square millimeter.
The size analysis performed shows a 5.2 mm margin on the height after meeting the requirement for the size of the cooling subassembly. The overall weight of the device was calculated to be about 0.56 kilograms, leaving a margin of 0.12 kilograms after meeting the requirement.
The unit cost of the wearable cooling device is $72.13. The Peltier module and the batteries make up the bulk of the cost. The operational duration test was performed by recording the temperature of the cold side of the cooling subassembly for 60 minutes. As shown in the graph, it decreased from 36 degrees Celsius to about 22 degrees Celsius over this time period.
The system requirement for user impact states that the device should have a heat flux of 0.11 watts per millimeter squared or more. Testing for the requirement consisted of cooling water inside a test cube with the device through a copper sheet interface by 10 degrees Celsius. Results are seen in the graph. The heat transfer equation 1 and heat flux equation 2 were used with the data obtained from the test to find the heat flux of the device. This was calculated to be 0.19 watts per millimeter squared, which meets the requirement.
In addition to the tests above, we had also planned to run a series of environmental verification tests, including an operational temperature test and survival temperature test, taking advantage of an on-campus climatic chamber. Additionally, we had also planned to run an emergency shutoff test that would verify that the fuse on the wearable cooling device would shut the device down if too much power was fed through. Unfortunately, due to the situation involving the novel coronavirus, we were unable to complete these 3 tests. The pictures below are of that of the climatic chamber at the University of Arizona's RISE Systems Engineering Lab.
The wearable cooling device is able to dissipate 0.196 watts per square millimeter. This is greater than the average amount of heat generated during outdoor athletic activities, which is 0.11 watts per square millimeter. It operates for more than 1 hour continuously, weighs less than 0.56 kilograms, it's smaller than 95 by 127 by 25 millimeters, and the unit cost is under $75. It has met all of the system requirements, and it will significantly help to reduce the risk of heat stroke and other heat-induced complications from occurring.
Now, Paul will demonstrate how to put on the wearable cooling device. First, turn on the side switch and slip the device on over your shoulders. Ensure that the straps are tight and the center buckle is buckled. There are 2 sets of adjusters on the side and shoulders to adjust the straps. If everything is good, the device will fit snug on the back, and you're good to go. And now Paul will demonstrate all the things you can do with the wearable cooling device, like running, attempting to play tennis, and even sorta kinda playing tennis. Nice work, Paul. Our wearable cooling device has met the requirements for cooling, size, weight, and cost. The device has the potential to curb heat-related illnesses here in Arizona and throughout the Southwest. We want to thank our mentor, Heather Hilsendanger, our sponsor, Dr. April Harris, and the University of Arizona College of Engineering for their support throughout this whole process. Thank you for watching, and we look forward to your questions.